So I don't know if it was fatigue, homework exercise fatigue, but this was one of the most missed regression problems. So I wanted to use it as an example of all the pieces that we are going through in chapter 10. So it says 50 matched pair of magnitude slash depth measurements randomly selected from 10,594 earthquakes recorded in 1 year from a location in Southern California. Find the best predicted depth of the earthquake with magnitude of 1.7. Use a significance level of 5%. And so they're waiting for us there. All right, so you can use Microsoft Excel, and I'll show you how you can do that. And I will show you how to do it with StatCrunch as well. So what we first wanted to do, if we were doing this from the beginning, we first would want to make sure that we could visually inspect the data and make sure that it had a linear, that it followed a linear pattern. Because we don't want to do a linear regression or lines of regression if they aren't linear. We have other methods to approach nonlinear forms. So I'm going to go ahead and copy to the clipboard, and I'll do a little paste of the data here then in Excel. I'm using 2010, I think, or 2007. It doesn't really matter. I don't think it matters that much. The first thing I'm going to do is I'm going to select just the data without the titles, and we're going to make a scatter plot. Okay, so I'm going to click on the Insert tab. I guess you should be able to see that a little bit here. Insert, and I'm going to choose a line graph of the scatter plot type. So let's see here. I'm sorry, scatter right there. So it'll insert the scatter plot. Now it's the scale here may make it a little bit more difficult to see. There are options, I think, here where we can choose to draw a best fit line already. But anyhow, going back to the original, it's hard to tell, but there is somewhat of a, there's definitely not a non-linear format, and there's some density of the points right here in this sort of a line, which they highlight here. All right, so anyway, I'm grabbing this data as it comes because I just grabbed the example of the homework problem, and I would have liked to see something a little bit better than that, but this is what we got. So we sorry about that. Pick a spot for the correlation coefficient. And I'll just put it right here. Equals, and the command is correlation. So I just start typing correlation just to see what comes up. And there it is. You can hit tab, and then it tells you the types of arguments that are necessary. Array 1 is what you're calling the X list, and then comma, array 2. And I'm just holding shift as I select all these. If you need Excel information, input help, then you can let me know. But anyways, you select the two arrays, X, Y, hit enter, and it's very small. Now, normally this is alarming to us, but remember, this is a set of 50 data. Now, the first row was the row that had the title. So this is actually the 50th pair. So this is a set of 50 data points. And when n is large, remember that, and I'll see if I can click on it here. I'll go to the page for it. Remember, if n is large, then the number that we need to beat is a whole lot smaller. Okay, so, and I'm getting this out of the approved notes. So I'm just going to go ahead and grab the fold out. That's probably fine. Okay, so n is 50 right here. We have to beat 2.79 if we are using a 5% level of significance. And what were we using in the question? We were using a 5% level of significance. did we beat 0.279? Get that to hold still. We got 0.262. A little low. like I said, remember that this wasn't really forming a nice linear shape that we wanted it to form. So I'm really not that surprised by that. I was hoping we'd still win with 50 pairs. But going back, we see we're shy of what we need. Anyway, the problem asks us to pursue the regression equation anyway. So it's really kind of beside the point when it comes to answering this question. All right, so sticking with Excel, we can now take this and do the rest of the calculations, which are found on these are one of the locations on the formula and table sheet. Under chapter 10, there's the R value that we just figured out. Not R value, I should say it correctly, the correlation R value. Correlation R number. R value actually has a different meaning. Anyway, and then we just need to figure out B1, B0, and then we can put together the line. But Excel has a way to save us some time from doing all these calculations too. So there's a little calculation function in Excel to find this B1 value, which is the slope of the prediction line, the regression line that we're going to use to predict Y. And I'll call it here B1, predicted slope. And it uses this function, a linear line. I'm going to go ahead and, as soon as you start typing one of these, if you don't know this already, you can hit tab and it'll select the one that's highlighted. Since there's only one highlighted, it obviously selected this lin est. And this is going to be a function that calculates statistics for using the least squares method. And that's what we want. And we're going to calculate it by putting in the known y's, because remember this is a prediction of y on x. It's how much can be predicted by the relationship of y on x. Okay, so then I selected each one, put a comma in between, and then the constant right here, since we aren't able to assume that it's set equal to 0, and it doesn't look like it's going to be, we're going to say calculate normally, and then I think we can leave off the last part, but I'll just see what they have. It says return additional regression statistics, do not return additional regression statistics. I'm going to go ahead and choose false to not return any, but I don't think it even matters. If I hit it, I get the 1.5939, which is our slope, our B1. If I said true, I'd get the same thing. And if I just left it off, no change. Okay, so what you want is, if you're going to use this line st, then choose the y's, then choose the x's in that order, and then say true to let it do the calculation, normal calculation for b. Okay, so that is the first part. And then looking at our calculations, and I'm doing it this way, even though there's another way, and I'll show you in a second. If you were looking carefully, you probably already saw that I have it up. There's another way to find the whole equation, but I'm doing it this way so you can kind of see through the calculations. To find B0, or B sub 0, we take the average of the y's minus B1 times the average of the x's. So the mean of the y's minus that value we just got times the mean of the x's. Or we could do this other one. Now, the reason why you often see two calculations is because if you're doing all this by hand and you've already figured out all these products and all these sums and all these squares of sums and squares, then you would find it easier to do this kind of a calculation. Because nowhere in the calculations that you've done so far did you ever have to calculate the average. And if the average was like a set of 100 numbers, adding all that together by hand and dividing that by 100 would have been more of a headache to do that for each coordinate, the x's and y's. So they have the shortcut. But I'm going to go ahead and use the calculation here. So the predicted intercept. Let's see. I'm going to need the mean, or the average in this case, arithmetic mean. I'm going to hit tab, select the function, select the data, make sure you get it all. Make sure you close that too with another parenthesis. That way this is just y bar minus, and then we want this value, so you can just click that value, or you can type in what the location of that value, C4, times the average again, and of the x's. So make sure you close it, hit enter, and there's your 8995. Now the question had asked us to round these to the nearest one decimal, so this is going to be approximately 1.6, and this one here is going to be approximately 9.0 if you're going to round those to the nearest one decimal. Alright, so those are the values we need to put in, and I've actually already put them in for us. So here they are, and it said that that part was correct. Okay, all this can be done very easily in StatCrunch. It also can be done much easier in Excel, and in fact I'll go ahead and show you what I already did. I don't know if you're looking at the right of this graph, but I right-clicked on one of the points, and I chose to add a trend line, and then I just choose the trend line option. We want it to be linear, since that's what we were trying to assume we had here. And we chose to display the equation on the chart. So I hit choose, and then there it is. Now I already snuck it over here earlier. I'll just delete that one. And you can make it larger, you can put it wherever you want in the area of the graph. And there's our explanation. Okay, so there's another part to this question, and then we'll use StatCrunch. Okay, so hit done. Given the earthquake has a magnitude of 1.7, the best predicted depth is, so now we're going to predict y, depth, by having x 1.7. So Excel's got a way to do this as well, and we want to predict y when x is, I like to make a separate field for the x value, that way I can select it and change it if I wanted to make a prediction for another x value, and find out what y is. So it is trend, yeah, so go ahead and go down to trend, or type the whole word in and type left parenthesis. You want to select your y's first again, because this is a prediction of y on x. Select your x's, comma, and then choose your new x's. These are the x values that you're going to use to predict against. So they'll basically just plug into this function, which we could have done by ourselves, and choose again to let b be calculated normally, and hit enter. So we got 11.705, and if we would have done it with the prediction line that we just found the pieces for, and I'm going to round using the 1.6 and the 9 that I had, I can do 1.6, whatever is in this cell from the estimation of this, which I didn't show you how to do that, so let me do it really fast. If you wanted to, you could have done the function, could have done it actually in the location where we actually did the line st calculation, but you can do it right here also, and you can say equals round, choose that, sorry, it's got to select, choose that, and then say how many places you want to round it. We're going to say 1 decimal. Similarly, we can do the same thing here. I'll just copy and paste. So then, that way, these will be changing when the data changes. In fact, I could use this whole sheet over again with a whole set of 50 different numbers, and everything would change automatically. Okay, if I set it up like this, I'm gonna choose this times the predicted value that I'm checking for plus this. And I get 11.72. They're going to ask me to round this to 1 decimal anyway. So might as well round it. It's the exact same 11.7 we really would have gotten there. Rounded it to 1 decimal, these are the exact same. All right, now if I plug that in, I would be wrong, and I'll show you what the answer is. I already plugged it in. It's not 11.7. Why not? Yeah, hopefully that pause was long enough. The reason why not is because remember that we can only use the regression equation for predictions of y on x if it has a linear correlation, or if we've checked and that r value is strong enough. So going back to the r value, and let me highlight that. We had 0.262, and our data set was 50 large. Remember, the first row is this says 51 because the first row is the title. And we checked already that if you're comparing for a set of size 50 with 5% significance, you have to beat 2.79, and we're talking about absolute value, obviously, so negative doesn't matter right here. 2.79, and we are 2.62. So what do you do if that's the case? What's your best estimate, your best predicted depth in that case? Do you remember? So it was in the text, but remember, you don't have the book during the test, so you don't have the textbook, but you do have all these highlights and handouts. So I'm choosing the one called Stat Review Card from the Dropbox, and it looks like this. And I am on, let's see here, I'm on the 4th page. And on the 4th page under regression, it talks about the regression equation, and it says when predicting the value of y, if no linear correlation, and that applies to what we just did because we had 2.62 and it needed to be above 2.79, what was it? 0.279. So that is us, no linear correlation. Then the best predicted y value is y bar. So it's the average of the y values. And let's figure out what that is. Now I actually used that in this calculation right here. I don't know if you can see. Let me just double click. That this right here is that same number. In fact, I'm just going to go ahead and copy this whole statement, paste it right there. Let's try that again. Let me try pasting it in here. And that is 11.486, so rounded to 1 decimal, that would be 11.5. All right. So all this done in Excel. It's a long video, you can go over it. I'm trying to do some lesson stuff too and show you how to use the handouts, you know, like the review card. I really like this review card. The formula sheet, I like you to know that you could do all this by hand. Not that I would want you to, and not that we have time for that during the test. But one more thing before we go, since I've already gone this long anyway, you could have done all this in StatCrunch. So open the data in StatCrunch. We have 2 questions. What's the equation for the regression line, and what is the predicted value when x is 1.7? So you just hit stat, regression, simple linear. Again, we're assuming that this, through visual inspection, has a linear pattern. If it doesn't, the nice thing about this tool is that it'll pop out the scatter plot for us, and we'll be able to inspect it after. So we're going to go through the numbers. I'll just go ahead, hypothesis test 0, 0, leave everything as it is. We're going to go ahead and stick in a predicted value right here, 1.7, and level significant, confidence level 95. And by the way, why would it need to know this level? Because remember how this level gives us alpha, which is 5%, and then we would have to let it decide if it was going to use the equation or not use the equation and instead give us y bar. Because remember how we chose to use y bar also because we realized that there wasn't correlation. We'll plot the line with it. Nothing else really, kind of ignore all the rest, I don't need that. And calculate. So it has here the line, look at that. Look at that, let me close this, put it all together on the same page. There's our 9 plus 1.6 times x. Okay, they're using the titles. You can actually relabel the titles to have x and y if it makes you feel better. It's actually better to use the names. Some sort of better identifier. Here's that r value, the 0.262 that we got in Excel. Here's our sample size reminder, 50. Here is r squared. That shows us how much of the correlation is of y on x, the percentage of it. It's only 7%. And then down here is the predicted y value when x is 1.7. Okay, hit next. And there's the graph, the one that we saw from the very beginning. Didn't look very, didn't fit a very linear visual inspection. It's kind of just all over the place. It's not something else. It's not like parabolic or exponential, but it's kind of just nothing. So I wanted to see if they worked that other piece out for us. So they do give us the prediction for y, but they're letting us use our own mind to recognize whether or not this is going to be used when the r value is too small. So for that last part, I think this is probably why this was the most missed question from the homework, from chapter 10. Probably because most people kept putting the 11.7, whether they were using Excel or StatCrunch, and they weren't thinking about the whole fact that if there wasn't a correlation, then we would use the average of the y's. Anyways, that's entirely too long of a video. Watch what you want to watch, pause what you want, that's fine. Thanks.